Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. Take a moment to gaze up at the night sky. Among those countless stars lies a mystery that has puzzled scientists for years. Why does our universe seem to be expanding at two different rates? It's as if the cosmos has a secret it hasn't been telling us. A tension between the early universe and the modern universe. We call this the Hubble tension. Here's the gist. When we look at distant stars and galaxies from the early cosmos, billions of years ago, our calculations show one rate of expansion. But when we measure things closer by, in the more recent universe, we get a slightly faster expansion rate. It's like checking the time on two clocks that should agree, and finding they're a bit out of sync. This is a big deal, because in theory, they should match up if our standard cosmology picture is correct. For a while, scientists have scratched their heads, wondering if new physics might be needed to explain this cosmic anomaly. Could our understanding of dark energy, the mysterious force pushing the universe apart, be wrong or incomplete? Did something weird happen after the Big Bang that we've overlooked? Over the years, a bunch of ideas have been tossed around to solve this cosmic conundrum. Some researchers wondered, what if Einstein's theory of gravity, general relativity, doesn't fully apply on the biggest scales? Others asked, what if time itself was behaving oddly in the early cosmos? Still others have speculated about exotic fixes, like early dark energy that changes over time, or even whether our entire concept of an expanding universe needs a tweak. One wild suggestion, maybe the whole universe has some kind of rotation or special structure that we haven't accounted for. So far, no single theory has emerged as the clear winner. It's an ongoing detective story in cosmology. Now, a new idea has joined the fray, and it flips the script in an unexpected way. Instead of blaming dark energy, the usual suspect, or rewriting gravity, a group of scientists asked, what if the culprit is actually dark matter? Dark matter is the invisible stuff making up most of the universe's matter content. It doesn't shine or absorb light, which is why we can't see it. But its gravity quietly holds galaxies and cosmic structures together. Typically, we've assumed dark matter is pretty vanilla. Some stable particle or substance that doesn't interact with much except through gravity. Oh, it's been our faithful, if shadowy, friend in cosmological models. But these researchers are proposing something bold. Dark matter might have evolved over cosmic time. In other words, the dark matter in the young universe might not behave exactly the same as dark matter does today. At first blush, that sounds almost heretical. After all, how can dark matter, presumably made of some fundamental particle, evolve? Particles don't usually change their spots. An electron 10 billion years ago was the same as an electron today. Yet if we consider the possibility that dark matter could undergo a transformation, or has multiple states, suddenly a new world of possibilities opens up. The researchers developed a model where a fraction of dark matter has a property that oscillates or shifts over time. Think of it like this. Imagine if some of the invisible particles out there had an internal clock or switch. Sometimes they behave one way, sometimes another, over billions of years. If this sounds speculative, it absolutely is. But it's grounded in an interesting analogy we already know in physics. We have particles called neutrinos, ghostly little particles that fly through your body by the trillions every second from the sun. Neutrinos actually do a weird trick. They oscillate between different types or flavors as they travel. One moment a neutrino is an electron neutrino. Then later it might turn into a muon neutrino, and so on. This was a huge discovery in particle physics that showed even tiny particles aren't always immutable. So, what if dark matter does something similarly strange? The new proposal suggests that maybe a portion, say, around 10 or 15%, of the dark matter in the universe cycles through different states that have slightly different properties, like different effective masses or the way they clump together. The rest of the dark matter, the other 85–90%, stays the good old steady stuff we're used to. But that small fraction of shape-shifting dark matter could have profound effects on cosmic history. When the universe was young, conditions were different, denser, hotter. And this oscillating dark matter might have contributed less or more to expansion at different stages compared to today. By the time we measure things in the local universe, that contribution might have changed. Here's why this is intriguing. If dark matter's effective behavior was a bit different back then, it could mimic the effects that we usually attribute to changing dark energy. Our standard model often tries to solve the Hubble tension by tweaking how dark energy works over time, since dark energy is what's driving acceleration of expansion. But dark energy is a very uniform, smeared-out thing. It's hard to make it do special tricks without breaking other observations. Dark matter, on the other hand, is clumpy and interacts gravitationally in complex ways. If a bit of it oscillates, it might reconcile the expansion rates by effectively acting like there was more or less push in the early era versus now, without needing to invoke a brand new force. The scientists behind this idea actually went further than hand-waving theory. They put numbers to it. They took cosmological data, all those measurements of galaxy distributions, cosmic microwave background, supernova distances, the works, and tried fitting their model of evolving dark matter to see if it explains the Hubble tension. And guess what? It turned out to be a surprisingly good fit. In their calculations, a universe where about 15% of dark matter oscillates in this funky way, and the remaining 85% is normal dark matter, can produce the differing expansion rates seen in observations. It's as if by giving dark matter a tiny bit of personality, the universe's behavior in youth versus adulthood falls into alignment. One way to picture this is, imagine dark matter as a hidden background orchestra, playing the music of gravity for the universe. We used to think the orchestra always played the same tune. But maybe in the early universe, a few instruments were playing a slightly different melody that made the tempo of expansion slightly slower. Over time, those instruments changed their tune, or quieted down, and the tempo picked up a bit, which is what we measure now. The end result is the same symphony we hear today, but with a subtle shift that happened over time. Now, it's important to stress that this is a new and speculative idea. It's a what-if that cosmologists are exploring, not an established fact. The researchers themselves call their dark matter model a kind of toy model, meaning it's a simplified idea to test a concept. It doesn't yet provide a detailed particle physics explanation of how dark matter would do this trick. In other words, we have a potential solution on paper, but we don't yet know what underlying new physics would allow dark matter to have oscillating behavior. That's an exciting open question. If this model is on the right track, what kind of new particle or mechanism could be at play? Could it be something like a very low mass, wavy field that interacts with dark matter particles, causing them to change state periodically? Or maybe dark matter particles have some kind of phase change under certain conditions. These are big unknowns. However, this evolving dark matter idea does something very valuable. It broadens our thinking. It says, hey, maybe we've been too fixated on dark energy as the only thing that could change. What if the dark sector, both dark matter and dark energy, has more complexity than we imagined? After all, dark matter makes up about 85% of all the matter in the universe. That's a huge component of reality, and we still don't know what it is exactly. We infer its existence from gravity, But we haven't caught a dark matter particle in our detectors yet. So while all our observations of galaxies and cosmic structure fit with the idea of dark matter being stable and not interacting with light, there might be hidden facets to it we just haven't uncovered. It's a bit like seeing the shadow of an animal in the jungle. You know it's there, and roughly how big it is from the shadow. But you don't know if the animal has stripes or spots. The Hubble tension could be a hint that dark matter has stripes, an internal dynamic that we never saw before. If this notion turns out to be on the right track, the implications are pretty profound. First off, it could solve one of the most nagging problems in cosmology in recent years, that Hubble tension keeping cosmologists up at night. Imagine that. With one elegant twist, the discord between early and late universe measurements fades away because we finally accounted for a hidden player in the game. It would be a eureka moment. Ah, the universe makes sense again. We just had to add this missing piece. Secondly, it would mean that the cosmos has a richer story over time than we knew. Whoa! The evolution of the universe would include a chapter where dark matter itself was doing something dynamic, not just passively sitting there. It kind of anthropomorphizes the universe in a fun way. Like the universe went through a dark matter puberty phase where things changed before settling into adult. Third, and perhaps most exciting, it would point scientists towards new physics. The ultimate goal in fields like cosmology and particle physics is to discover something genuinely new about how nature works. If dark matter evolves, that's new physics. It could spur laboratory experiments or astrophysical observations to catch dark matter in the act of oscillating. Perhaps we design new detectors, or reanalyze data from telescopes, looking for subtle fingerprints of this behavior. Maybe in how galaxy clustering works, or how certain cosmic signals propagate. For example, if some dark matter oscillates, could it occasionally interact differently with regular matter? Would there be tiny periodic distortions in cosmic microwave background patterns, or in the distribution of galaxies that we could seek out? Researchers would definitely start devising tests. Science is all about testing ideas, and a good theory is one that makes testable predictions. Right now, this evolving dark matter model needs to flesh out predictions beyond solves the Hubble tension to things like, here is how we can confirm it observationally. Let's take a step back and appreciate the creativity here. We often think of scientists as rigidly sticking to established theories. But in reality, when presented with a puzzle like the Hubble tension, they can get really imaginative. They essentially ask, have we tried turning dark matter off and on again? Like it's a cosmic solution. It's a reminder of how little we truly know about the dark 95% of the universe. About 70% is dark energy, 25% dark matter, and less than 5% is the normal matter that makes up stars, planets, and us. We've been in the dark, literally, about the nature of most of what's out there. So maybe we shouldn't be shocked if it has surprises in store. Now, maybe down the line this idea will turn out to be wrong or incomplete. That's okay. It's all part of the process of scientific discovery. Even if this specific model doesn't hold up, exploring it will undoubtedly teach us more. It will force researchers to gather more precise data on cosmic expansion, on the cosmic microwave background, on large-scale structures, to see if they can catch any sign of dark matter's alleged evolution. And if the signs don't show up, that's a clue too. It might strengthen the case that something else is at play, maybe back to the drawing board with dark energy or other new physics. But let's say, just for fun, that in a few years we accumulate evidence that yes, dark matter does this weird oscillation dance. How mind-blowing would that be? It would mean the basic makeup of the universe has layers of complexity previously unimagined. It would rewrite textbooks in cosmology. Fine. And it might even have practical implications for the fate of the universe. For instance, If dark matter's role changes over time, it could affect how we predict the ultimate end of the universe. Whether it expands forever, big crunches, or something even stranger. One of the exciting implications the researchers noted is that if dark matter, rather than dark energy, is doing the evolving, then dark energy might actually be a constant after all. Right now, we call dark energy something like a cosmological constant in our equations. Basically, a fixed energy of empty space. But we've had to consider that it might not be constant to explain certain data. If this model holds up, dark energy could go back to being a simple constant property of space, and instead dark matter's history would carry the burden of explaining the anomalies. That would simplify some aspects of theory. A constant dark energy is easier to handle than one that morphs, but complicate others. Now we have complex dark matter. Either way, the universe isn't obligated to be simple for our benefit. In the grand scheme, this line of investigation is a beautiful example of scientific curiosity and open-mindedness. It shows that even pillars of our understanding, like dark matter being unchanging, are not beyond question. The nature of dark matter has always been one of the biggest open questions in physics. We built gigantic underground detectors to try to catch a whiff of it. We smash particles together in colliders, hoping something will pop out, and we tune telescopes to observe its gravitational effects. It has consistently evaded direct detection, which hints that it might not interact in any straightforward way with normal matter. If it also has this chameleon-like oscillating trait, it's no wonder it's been elusive. It's like trying to hit a moving target. Ultimately, whether or not this particular theory pans out, it fuels our sense of wonder about the cosmos. Could the invisible substance that holds galaxies together also hold the key to a cosmic mystery by changing over time? It's almost poetic. Something utterly dark and unseen, quietly evolving and influencing the fate of everything. It reminds us that the universe still has secrets up its sleeve, and we humans are just beginning to peel back the layers. So the next time you look up at the sky and ponder what's out there, consider that even the invisible parts of the universe might have a story, a life cycle, or an evolution that we are only now guessing at. How many more creative twists might it take for us to fully understand the cosmos we call home? And if dark matter can change over time, what does that say about the certainty of other cosmic constants? It's a humbling thought, one that keeps astronomers and physicists eagerly watching the skies and their computer screens, chasing whispers of the universe's truth. If the idea of evolving dark matter makes you wonder what other cosmic surprises await, you're not alone. The universe has taught us time and again to never say never. So, what do you suspect might be the next big revelation about our cosmos?